Brilliant. Thank you very much, Batul. And yeah, thank you very much for inviting me to talk to everyone today. I'm really looking forward to it. The eagle-eyed amongst you might have noticed a very slight change to the title of my talk. So today I will be talking about explaining the unexplainable, the paradox of explainability in the development of artificial intelligence. Yeah, as you've heard, my name is Duncan Reynolds, and I am a postdoctoral research associate of social science based at Queen Mary University of London, down in East London. And I am part of the AI Multiply project as part of kind of the NIHR funded AIM consortia. And I'm a qualitative researcher who specializes in ethnographic approaches. And don't worry if that doesn't mean anything to you, I'll go into it in a little bit more detail in a second. My PhD before I joined this project was on the development of trust in clinical trials. And this kind of idea of trust is something that I've also taken forward into my postdoc work. Trust when it comes to AI, especially AI in healthcare, is something we hear a huge amount about, and it comes up constantly, and it might come up today. We'll see. If you want to distract me at any point outside of academia, I'm a keen triathlete, so any conversation around VLA maxes or VO2, anything like that will really get me going on a different subject. So if you want to distract me, that's all you need to talk about. So we have, from what I understand, quite a range of people here attending today, which is great. But that also might mean that sometimes I might say words that don't necessarily mean something to everyone. If I do say something and you don't quite understand what it is, or you'd like a bit more explanation, please chuck it in the chat. I've got the chat so I can see that as well as my slides. So I will see that and I will try and explain. But just by a very quick show of hands, who here has heard of ethnography or knows what ethnography is? Just, quick hand up so I can just have a rough idea. I'm yeah, perfect. I can see. Great. That looks like about a third of the people that I can see have their hand up. Perfect. So ethnography is a qualitative approach to research. And yeah, I won't go into the kind of ontological, epistemological underpinnings of it. But with this approach, data is collected through observations and interviews, amongst other things. And by observations, I mean physically being there in person during things like meetings or maybe sitting in hospital appointments, depending on what you want to observe, and sitting there and observing and taking notes of what it is that is happening. And by doing this very on the ground, kind of fly on the wall observation, what ethnographers such as myself attempt to do is make the invisible visible. And we have a real interest in the particular, the actual grounded lived experience of what is happening rather than the general high level. We are interested in the particular of what is going on. And so you might be thinking, oh, but AI in healthcare, such as, what AI Multiply is working on as a project, that's all data scientists and clinicians. What kind of questions could a social scientist or an ethnographer, someone interested in these very particulars, what kind of thing could they answer on this project? Well, what I do, and part of what I do, is I do ethnographic observations to try and answer questions such as how do interdisciplinary teams work collaboratively to create ideas, discussions, and negotiate disagreements to build consensus when creating technology? Or how do different ideas and beliefs become built into technology in practice? And how are matters of ethics and governance negotiated in AI? These are the sorts of questions that I am interested in as an ethnographer. So, what am I going to be talking to you all about today? I'm going to be talking about how on AI multiply, and I will talk a little bit more about what AI multiply is later for those who don't know, how there is some of the AI which is being built or used on this project, and how they are attempting to make these models explainable. And again, I'll talk more about what we mean by explainable in a minute. I will talk a little bit about kind of the theoretical framework that I use to understand what is going on. And in this case, I'm using paradox theory, understanding paradoxes as they occur. I will talk a little bit about the model that we are attempting to explain, and then I will map out some of the paradoxes which have emerged in the attempts to make this model explainable. So again, I'm just going to ask everyone, like I did with the ethnography question, I'm just going to ask, if I said to you, artificial intelligence is a black box, does that mean anything to you? And if it does, do you mind raising your hand, just so I have an idea? I'm seeing hands go up fairly quickly, so I'm taking that as a sign that people have an idea. I'm seeing thumbs ups as well. Okay, cool. More people seem happier with the idea of artificial intelligence as a black box than they were with the idea of ethnography. So this has given me an idea of, the kind of audience I have, which is great. It's really interesting. So artificial intelligence being a black box at a very basic level would mean that we can know what we put into an artificial intelligence algorithm, the input, the data. It might be your prompt you're writing into ChatGPT. And we know what the output is that we get. It might be the answer that ChatGPT gives you to your prompt. We can understand, we know the input, we know the output, but what is happening in the middle to turn your input into an output is a bit of a mystery. And it is a black box. We don't fully understand what is going on inside the algorithm. It's kind of almost one of the key features of artificial intelligence, that we don't necessarily fully understand what is going on the inside. We can know the inputs and we can know the outputs, but the middle is a mystery. And according to Shortlift and Sepulveda, having these black boxes in healthcare is unacceptable. When important issues such as our health should not be being decided by algorithms that we do not fully understand how they work. And we don't need to go through it all, but I've put some literature on the slide there with some arguments about why these black boxes are unacceptable. There's arguments about trust. How can we trust something if we don't know how it works? Or how can something be accountable if we don't know how it works? How do we know something isn't being biased or discriminatory if we don't fully understand how it works? But not everyone agrees that artificial intelligence in healthcare does need to be explainable. There are quite a few arguments from people saying that actually the problems we have at the moment in healthcare systems, not just in the UK, but around the world, are so profound and difficult that if artificial intelligence is looking like a positive solution, it doesn't matter if we don't understand how it works. It's a solution. Why are we saying no to progress? And other arguments such as, well, I don't actually know what's going on inside the head of my doctor. A human is a black box as well. So why is it any different that an algorithm is a black box? Isn't it essentially the same? So we do actually have arguments on both sides. Not everyone believes that artificial intelligence being a black box in healthcare is a bad thing. But still, there are large calls for artificial intelligence in healthcare to be explainable. So when we talk about artificial intelligence being explainable, this can mean lots of different things. And the way that most people understand the term, and the term is often referred to as XAI, explainable AI, is often spoken about in very technical terms, applying technical methods to make the artificial intelligence explainable. And slightly more specifically, we are often talking about what Lipton calls post hoc explanations, which tell us what the artificial intelligence model has deemed important. That I mean, I don't come from a technical background. I come from a social science background. So when it was explained to me in those terms, it didn't necessarily resonate with me until I was shown this image, which I will run through now because it really helped me understand what was meant by explainable AI. And one of the things that artificial intelligence is pretty good at is clustering, categorizing things. And you might create, as in the example of this picture, an artificial intelligence system which is saying whether an image contains a cat or a dog. And you will put all your images in and it will sort them into cat, dog, 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 cat. And at the end of it, you can look at it and say, great, the model was 99% accurate because that's a cat, that's a dog, that's not a cat, but that is a dog. And you know whether it's got the answer right or not. But what you don't necessarily know is why it has chosen that as a cat and that as a dog. You just know that it has chosen them as a cat and a dog. But you can apply an explainable technique to understand what has made the algorithm choose cat or dog. And that's what this image is showing. It's a system called GradCam, which overlays a heat map onto the image and shows what it is that the algorithm has chosen to be important when classifying cat or dog. And in the middle image, we can see the algorithm has kind of focused on the abdomen of the cat to say this is a cat. In the third image, the dog, it is really focused on the face of the dog to say that is a dog. And we can look at that and we can be pretty comfortable that our algorithm is saying something is a cat or a dog based on it being a cat or a dog. If, for example, the heat map had been on the window for the dog, we might have thought, you've correctly said that it is a dog, but for completely the wrong reasons. And we need to go and rethink the model. And there are very famous examples, especially from the US military, of times where they think they've got a really good classification algorithm, but actually it's picking up on completely the wrong things. Probably don't have time to go into them now, but there are some interesting US military examples if you want to Google how they've got it wrong in the past. So very briefly, I didn't really know where to put this slide, but I'm going to put it here. I've argued briefly that kind of artificial intelligence in healthcare can't be a black box, but not everyone agrees with that. On the AI Multiply project, I wanted to understand whether people thought it was important to have artificial intelligence as a black box or whether it should be explainable. So in my interviews, I asked people about the importance of whether they thought it was important to have explainable AI. And broadly, pretty much everyone said yes, it was. And the data scientists came back in their interviews saying it is important to the clinicians. And then it is important for us to explain to lay people and the patient public involvement group. The clinicians came back saying there is no doubt that the patients and public want explainable AI. When interviewing patients, what came up was things like, it doesn't matter if I can explain the algorithm, it's whether the doctor can. So across these different kind of groups with different interests, there was a real understanding or real belief that explainable AI was important. But what some of you might have picked up on from these quotes is that explainable AI is always important for somebody else. No one is saying here, AI needs to be explainable for me. The data scientist said it was important for the clinicians. The clinician said it was important for the patients. The patient said it's important for the clinicians. It is always important for someone else, which is an interesting thing to kind of emerge from our study so far. Need to see where it goes, but it's something worth keeping in mind that on our project, we do think explainable AI is important, but it always seems to be important for someone else. Keeping half an eye on the clock. Okay, I'll speed up a little bit. I've spoken about explainable AI in quite technical terms instead in terms of this is an algorithm that you can explain by applying a technical technique such as GradCam to it. Well, actually, some people believe that explainable AI can be thought of much more broadly than this, and limiting yourself to just explaining kind of the model doesn't take into account that different people want different things or understand different things when they talk about explainable AI. Some people might want the features importance ranked, and to them that is explainable. But to other people, it might be having correct inputted data might be what's important to be explained. And instead of thinking about this as something purely technical, instead we should think of it as something socio-technical. And what that means is that the technical and the social are never fully separate, but they are constantly entwined together. What is technical impacts the social, what is social also impacts the technical. We need to think about what do we want to be explainable and to what audience. It's never just as simple as saying, oh, it's purely technical, that's it. There is always a social aspect as well. And hopefully you'll see that as I carry on through my talk. I said when I started, what was it, about 15 minutes ago, that I am using paradoxes as kind of a theoretical framework to understand my data. And the idea of this is that healthcare and healthcare organizations exist in an incredibly complex, high stakes environment, that there is a constant need to balance competing demands. And when you need to balance competing demands, paradoxes emerge. Paradox theory kind of tells us that actually paradoxes aren't things that need to be solved. We don't look at these competing demands clashing and think, right, which one is correct, A or B? That's not how it works. Instead, we conceptualize them as dynamic tensions that have to be managed over time. And Smith and Lewis, who are kind of quite famous paradox scholars, talk about a dynamic equilibrium between these competing demands that shift and sway over time, and organizations have to manage them. And we can see these kind of paradoxes every day. I'm sure if you went onto BBC News or switched on the Sky News or something now, there would be news stories about how we want better public services, we want quicker access to healthcare, better drugs available to us, but at the same time, we need efficiency. We need to reduce taxes. We don't want to have such a burden financially upon everyone. And this could be seen as a paradox. Perhaps lower taxes and higher public services potentially could be seen as something which needs to be managed in this dynamic equilibrium. And society deals with this kind of, you can almost see it in election cycles by depending on voting for different governments who have different priorities or manage things in different ways. So these paradoxes exist constantly around us and are in kind of dynamic equilibrium, and we have to understand how to manage them. So what does this all mean in the context of trying to create explainable AI? Well, some literature has already looked at this. I forgot about this slide. When looking at artificial intelligence in healthcare, some people have already spotted lots of paradoxes that exist. I'm not going to go through all of these, but Cannelning writes about the paradox of inevitability, saying AI is the future. Everyone is talking about all this new money. Everyone is going to be using AI. We must push forward. It is a fantastic future resource that we must use. But also, we have lots of people very nervous about artificial intelligence, partly because it's not explainable, partly because it might be biased, it might increase discrimination, it might lead to loss of jobs for people. It is a leap into the unknown. So we have this, oh, it's fantastic, great advancement, but also great worry and skepticism clashing together in this paradox of inevitability. We have problems, but it looks inevitable that it's going to happen anyway. Hoover talks about datafication paradoxes, where policies which aim to kind of make everything into data were aimed to make life simpler. If something is data, we can't question that. It's just what it is. Think back to the Sociotechnical. Maybe it's not that simple. But if we have datafication making life easier, but suddenly all of this data needs to be interpreted in new, different, complex ways. So actually, data practices have made it more difficult. So datafication, to make things easier, has actually led to data practices which make things harder. These are some of the paradoxes which emerge with AI. So, how can using the idea of paradox help us to understand the development of explainable AI and what paradoxes emerge when creating explainable AI? And how can we manage these paradoxes to achieve shared goals? That's what I'll be talking about for the final kind of 10, 15 minutes of my talk. I said that I am part of AI Multiply, which is a NIHR funded project, which is attempting to use AI to untangle the complex interactions between people with multiple long-term conditions who are on multiple medications. And it's an interdisciplinary team consisting of clinicians, pharmacists, data engineers, AI modelers, biostatisticians, social scientists such as myself, a large patient and public involvement group, and more. There's a huge number of people and interdisciplinary groups represented in the team. I am doing ethnographic observations of this. So I am observing the interdisciplinary meetings that happened, and so far I've got about 170 hours worth of notes that I'm ethnographic data of this. I'm also interviewing members of the team. I've done 19 so far, and they are ongoing. I take the data that I have from the team, and in reflexive workshops, I show it back to them, which is always fun, getting people to watch what they are doing back and getting themselves to think about their own practices in very reflexive ways. That can always lead to interesting areas. And specifically today, I'm going to be talking about what has kind of become known in the group as the readmission model. And the readmission model is one of the AI models which is being created by the team. And it's a model to predict non-planned emergency readmission to hospital after first being in hospital within 30 days. And a few different kind of AI techniques are being used whilst making this model to kind of compare and contrast and see which one's best. A supervised simple neural network, complex neural network, and a self-supervised learning model. As I said, I am not a technical AI person, so if you want really, really in-depth answers on the differences between those three different kinds of model, I can only provide a very basic one, so I will not be the person to ask for complex AI questions, I'm afraid. And when creating this model or these models, technical approaches to understand them, such as techniques known as SHAP and ablation, we'll go more into SHAP later, so don't worry about what that actually is now. These were technical tools like GradCam, which are applied to a model to try and explain what is driving it. As well as using these technical explanation tools, there are also lots of interdisciplinary meetings to discuss the results and the developments. From these meetings and from these technical solutions, paradoxes in three broad areas have emerged. The data being inputted into the model itself, and the outputs to the model. And that's what we're going to look at in the final little bit of this talk now, the paradoxes that have emerged. I will warn you, the next, I think it's 5 or so slides, because it's ethnographic qualitative data, they're very wordy. What I don't want you to do is try and read every word that is on the slides. These slides will be sent around later, I believe, and the talk is being recorded, so you can kind of pause later and read it all if you want. I will highlight the important bits, but because they are quotes from interviews and quotes from ethnographic observations, they're quite dense. So I apologize. I know it's not going to be very pretty. And I didn't lie to you. It's not pretty. So the first paradox that I would like to talk about is the clash between accuracy versus power in the model. And this emerges when thinking about the data that is being inputted into the model. And we have an interview here from a data scientist who said, actually, when we worked on the readmission model, we used a data set and we had very good results at that time. We had very good results, especially for the unsupervised model. But then we realized that the data is not actually fulfilling the questions or concerns of the clinicians. And in that case, we had to revise the data set. So at that point, I realized they, the clinicians, don't focus mostly on the accuracy. Yes, it's important, but this is not the main point. Kind of dot, dot, dot. Once we revised the data and then fed it into the model, we didn't get that much result, but we didn't get a good result compared to the previous one. So what happened here is that a model was created, a data set was inputted into the model, a result came out, and the data scientists were delighted. The model had fantastic results. They couldn't believe their luck. They thought it was great. The clinicians asked some questions around the data set. They wanted the data that was being inputted to be explained to them a little bit more, to make sure that it kind of reflected their understanding of healthcare in practice and what was going on the ground. And after this discussion, the clinicians weren't very happy with the data that had been put in. They said, no, this doesn't reflect our clinical practice. What we would actually like to do is change the data set and then run the model again. So they did. And the model came back less accurate, much to the dismay of this data scientist, who couldn't understand why you would want a less powerful model. The data set they originally used was great. Why have we changed it? It had a powerful model. But the clinicians said it wasn't accurate to their practice. It was changed, the model was less powerful, but now the clinicians were happy. So in this kind of little tension between accuracy and power, the clinicians won out in the end. And it was perhaps the less powerful model, but perhaps more reflective of practice, that won. And we can see a tension that emerges from this paradox of accuracy versus power. And that's the tension of how do we actually reify everyday practice as data? How do we take something as complex as social interaction, or even something as complex as your interaction with a GP, because that's where this data comes from, and turn it into simple data? And we can see a different data scientist saying, I know it's clinical data. There are so many subjective decisions. We think of data as hard truth, but actually it's anything but. It is a decision made by someone of what to code, a decision of someone what to include in the model, and a decision of someone how to interpret it. And another data scientist said, whilst talking about kind of patients and data, I know you through a record containing 10 numbers. This is not you. It would be offensive, but that's what we have. And I think we did reach the conclusion that many of the models that we've built are not realistic because the file, the representation that we have of individuals is not realistic. It's far too simplified. So we can see this tension between practice and reality as part of this wider paradox of accuracy versus power. Moving on to the second area where we've seen the kind of paradox emerge. With the model itself explaining the unexplainable. And we have a different data scientist, data scientist 4, I've called them here, just talking in quite general terms that one of the main differences between artificial intelligence and traditional statistical methods is that with traditional statistical methods, if you are that way mathematically inclined, you could sit there and work out all the maths yourself, go through it all, and it would, it might be difficult, might take a long time, but it would be possible. With artificial intelligence, that is damn near impossible. Either the numbers are just simply too big to ever be done in a lifetime, or it is not actually possible because you don't know what routes the artificial intelligence is taking. It is a black box by nature. So we know that artificial intelligence is a black box. And yet, as we can see of the quotes at the bottom, we still try and use methods to explain it. And as we can really see in these quotes, even when we know the methods themselves might not be very good. For example, the quote in the middle. There is a lot of skepticism about the methods, the explainable methods. What are they capturing, these explanatory methods? The Shapley values have been around for some time, very exotic, except for people in certain circles. They're not super easy to interpret, but they're also not super easy to believe, because again, I mean, it's an analytical tool. So we're starting to see a paradox emerge here of we have something that we know is unexplainable, and we have tools that we don't necessarily think are doing what they say they're going to be doing. And yet, as we see here, again, you don't need to go through it, I'll highlight the pertinent aspects. We spent a lot of time debating which explainable method should we use to try and explain the unexplainable. And this is kind of a little bit of a transcript from a meeting where a data scientist was saying they had a problem that they tried a few different explainable techniques, and every time the explainable technique said that different features were important in the model. They never got the same results. And a clinician was saying, well, that's not surprising because you're using different models, so it's going to deal with the data in different ways. But the data scientist, perhaps struggling with the idea that there wasn't an answer out there for what is the correct explainable tool, because all these tools were giving different results, led to a discussion about, well, we just need to pick one. Whichever one we can justify and whichever one we feel is doing the job the best is the explainable tool that we will use. So we have a paradox trying to explain the unexplainable, where we know it's a black box. We know the tools themselves aren't great, but we put a lot of effort into debating which tool we should be using and deciding which tool we should select to explain the model. And in the end, a version of SHAP was used, and this is some of the results. That's all blindingly obvious to everyone, I'm sure. I don't need to spend any time explaining what any of that means. Or perhaps we remember the quote on the last page, which said that these things need a lot of interpreting. We're not going to spend a lot of time sitting on this interpreting it, because that's not quite the point of what we're doing. It's just to highlight that when some explainability tools were applied to the model, this one is called SHAP, and it ranks the importance of the features within the model, and it says whether it has a positive or a negative effect. So in this case, for the readmission model, the most important feature was age at event. And blue to the left suggests that if you are younger, you are less likely to be readmitted, and the red to the right suggests that if you are older, you are more likely to be readmitted, which I guess would intuitively make sense. You would imagine people who are older are more likely to be readmitted to hospital in an emergency setting. But not everything was as simple as just the age one, which comes out at the top. And actually, there was a tension, which I've called an epistemic tension here, so a tension in knowledge. Sometimes, such as with age, the model came out with an explanation which fit known medical knowledge. And when it fit known medical knowledge, everyone was happy with it. Sometimes the model came out with something that did not fit known medical knowledge. And this is where the tension and the paradoxes emerge. And I'll read the first quote because it kind of talks about it quite well. The irony with this explanation business is that typically experts, doctors in this case, will look for confirmation because they're very well trained in what they know. And so one or two things happens. Either the explanation confirms what you already know, and so it's very reassuring, but you haven't really discovered anything new, or it doesn't. Then in which case you go into the conflict phase process. It is something new that I don't know, or it is something not credible because I have the truth and I have the perfect training. They get defensive. Doctors get defensive very quickly. So what that is saying is the doctors were happy when they understood what was going on because the explanation conformed to their knowledge. But when the explanation did not conform to their knowledge, there was pushback. And part of the point of using artificial intelligence is to get us thinking in ways, or create knowledge that we did not know before. And suddenly, when this new knowledge is being created and brought out there, it is being pushed back against because it doesn't conform to our current knowledge. This is the kind of tension that's happening. And you can see that in the little excerpt from the bottom. So a clinician saying, it's to do with the interpretation and the slightly surprising ones. The estrogen, the HRT, NSAIDs seem to be in the wrong direction, or the more surprising one. The other one is body fat. If I am reading this correctly, then lower body fat. Am I reading this right? A lower body fat is associated with a higher rate of readmission, or a lower rate of readmission. It's the former. Lower body fat points to a high rate of readmission. Again, this is surprising. It is the other way round than we might predict. So this doctor saw on this graph here things like body fat, and it's because the red is to the left, that's positive. So lower body fat, more likely to be readmitted. Blue on the right, more body fat, less likely to be readmitted, is the wrong way round to their medical knowledge. And the new knowledge which is being created from the AI that is being explained didn't conform to what they know, and there was a battle around it. So I'm mildly aware that I've gone through quite a lot of information, some of it quite technical, very quickly. So I do apologize for that, but I would be more than happy to talk through this in more detail with anyone at any point. But hopefully, what we've kind of seen here is that attempts to make artificial intelligence explainable firstly require a huge amount of interpreting work. These models don't just speak for themselves. The data you input isn't just data, it has to be negotiated itself. And we have to resolve these contradictions and perhaps start framing explainable AI rather than some objective truth, the model is now explained, but actually it's a negotiation process between people from a technical background, clinical background, patients, regulatory actors, etc., about what it is to be explainable and where do we want to sit on some of these dynamic equilibriums of the tensions, power versus accuracy, explainable versus unexplainable, knowledge versus new knowledge versus old knowledge. And perhaps by doing this, we can kind of shift from thinking of explainable AI to perhaps how we co-construct meaningful explanations with relevant stakeholders. And from this, we might understand that explainability is very context dependent. What is explainable for one group might not be what is explainable for another. And I will end it there. Thank you very much.
Thank you so much, Duncan. I'm going to take over chairing because Batul's internet is not doing very well today. So thanks so much. I'm going to say